So this is going to be a pretty informal update. I'm sharing this via a poster that I made for the AGU conference, the American Geophysical Union, which is happening this week. I unfortunately could not attend. So I will walk through this. The context for this is it's included in the online gallery for the conference. And so there's a bit more text than I think we would normally include in posters because I'm not presenting it in person. But there's some cool features for the iPoster, so we'll walk through the research and hopefully give you guys a good overview of what I've been working on. These are kind of mostly the results that I had shared in the spring in June with some additional results, and then we'll spend a little bit of time on future work as well. So starting out with some background. So exoplanet research is very critical both for putting our solar system in the context of the universe and understanding the uniqueness of it, but also to understand if there are other planets out there that have the potential to support life or currently support life. So the past decade has seen kind of a proliferation of exoplanet discoveries. However, they've been mostly through indirect methods. So we take measurements of the host star, and based on those measurements can infer the existence of an exoplanet. And so now, if we want to get more information about the planets, such as the biosignatures and the atmospheric characterization, we actually need to move towards direct imaging, because indirect imaging is really limited to giving you like the mass and the radius of the planet, but it can't really give you spectral characterization or any detailed information about the planet's atmosphere. So we need to kind of move to direct imaging if we are interested in discovering the potential habitability of other worlds. And so with direct imaging, there are a few kind of promising techniques for starlight suppression. So one of the biggest challenges for direct imaging is that the exoplanet is significantly dimmer than its host star. And so in order to be able to image the exoplanet, we need to suppress the light from the host star to increase the contrast of the resulting image. And so we've seen starshade, many proposed starshade missions over the past few years that vary in size. If you guys are familiar with MDOT, of course, here in SLAB, the miniaturized distributed Folter telescope, as well as ranging to several orders of magnitude larger starshade mission concepts. And so these vary in size and also mission objectives. And so here is kind of an image of, I'm sure you guys are familiar with this. This is MDOT, which was a 3-meter tip-to-tip starshade Folter versus some of the ones that were studied for, like James Webb, for example, were on the order of 30 meters. So we've established direct imaging as a key technology area that we want to develop for exoplanet science. And we've established starshades as kind of a promising technology for starlight suppression. However, even with the starshade, the performance that starshades can give us, direct images are still incredibly noisy. So there's several sources of astrophysical, optical, sensor, instrument noise that confound the planet signal in the image. And so you can see this, so these are two representative synthetic starshade images. And so it's the same image on the left and the right, and you can see that there are two exoplanet sources in this image, which are identified by the red boxes on the right. However, if you look at just the image on the left, there's no way that you could actually disentangle where that planet is in the image. And so we refer to this as low signal to noise ratio images. Essentially, the noise in the image, which again, there's several sources of, confounds the signal. So the resulting signal is very minimal compared to all of the sources of noise. And since we're limited in how much performance we can get from our actual, physical hardware, we have to rely on post-processing techniques in order to process these images. And so image processing algorithms are essential in order to be able to harness the information that we can get from direct imaging. So with image processing algorithms, the state of the art is using these multi-step pipelines using principal component analysis and then additional filtering to get down to identifying the exoplanet sources. This requires a lot of manual tuning and it's very time intensive. And so when we move towards these direct imaging missions where we're going to be getting massive amounts of data, it's not really feasible to be able to process all of them using these manual techniques. So machine learning, of course, has been used very extensively in a lot of image processing applications. And so it's a robust and efficient alternative. However, because we have such limited data for direct exoplanet images in general, and especially star shades, we have not been able to really explore this opportunity prior to now. So when we move to the deep learning approach, the objective of this research is then to kind of explore using convolutional neural networks for exoplanet detection, specifically from starshade images. And so when we talk about convolutional neural networks, just a high-level overview of, machine learning algorithms and CNNs in particular. Convolutional neural network, the model is made up of a feature extractor and a detection head, which is the feature extractor and the detection head are composed of learnable parameters. So the idea is that if you have a large amount of training data, you can feed it through your model, compare the output with the known true output, and use that to feed updates back into your model. And so that is the training pipeline. And then once you have a learned model, the inference pipeline is very efficient, where you can just feed in images to the model and it outputs your regressed information. And so, like I mentioned, convolutional neural networks have been applied very extensively to many computer vision problems, namely in SLAB. We have, of course, Jeff's work, which looks at spacecraft pose estimation using machine learning, but it's also been applied very extensively to autonomous vehicles, robotics, even in the medical industry for examining X-rays and such. So it's a very well-studied approach that we're hoping to adapt to this application. And so as a proof of concept, to kick this work off to understand the capabilities and the constraints of applying machine learning to starshade images, given the fact that they are so low signal to noise, we first explored using YOLO V3, which is a state-of-the-art object detection CNN, which uses bounding box regression. So it regresses the centroid and the width and the height amongst other parameters of objects in the image. So here are just the training parameters that we used for YOLO V3. These are pretty standard parameters in terms of number of epochs and batch size. The loss function is generalized intersection over union, which is essentially looking at like it mentions, the intersection of the predicted bounding box versus the ground truth bounding box over the total area encompassed by the two boxes. And so, as I mentioned, kind of the key constraint to prior machine learning applications has been the data set. Or the lack of data. And so what really enables this research is the Starshade Imaging Simulation Toolkit for Exoplanet Reconnaissance, which is a bit of a mouthful, or SISTER for short. So this is a new Starshade image simulator that JPL has created. And essentially what it does is it allows a user to input various astrophysical parameters to create a scene, and then that astrophysical scene is convolved with a model of the starshade and the optical system in order to produce a simulated starshade image. And it accounts for several sources of noise, as well as allows you to vary the bandwidth that you're simulating in the image. And so this is just a GIF of what SISTER can produce. And so the data set that we're using was also actually generated by JPL using SISTER. And it was generated they hosted a Starshade Exoplanet Data Challenge where they created a data set and basically chose teams to compete to create algorithms that could process the images. And so the data set is still relatively limited compared to machine learning applications. There's about 1,450 images in the data set. And so when we were training the neural network, we had to incorporate data augmentation using random cropping and rotations and flips in order to artificially expand the size of the network for training. And so driving down into just a little bit more detail of what all is encompassed in that data set. So in terms of exoplanet configurations, it is modeled using 10 known stars with 10 various configurations of exoplanet systems. We are modeling the star shade contrast both at 1e to the -10, which is kind of the nominal star shade performance, as well as a degraded star shade performance, using 2 different pass bands, as well as several levels of noise, both in the exozodiacal dust, which for the sake of exoplanets is a source of noise, but in its own right is also something we're interested in studying, as well as the signal to noise ratio of the overall image. So moving on to results. So these are probably most well displayed using actual images showing the CNN predictions versus the ground truth predictions. So the ground truth being the actual location of the planets in the images in the white boxes, and then the YOLO V3 predictions in the red boxes. And so you can see also the diversity of some of the images contained in the data set here. So on the left and the right, you can see the right images are much grainier, much noisier, and that's because it is modeling a much lower signal to noise ratio, versus on the left, we have a higher signal to noise ratio, which shows a little bit clearer in the image. Still, obviously not very easy to detect the exoplanets visually, but we've seen pretty good performance so far with the CNN being able to disentangle the noise. So tabulating some of this. So the metrics that we're primarily using right now are precision and recall, which is the ratio. Precision is the ratio of the true positives, so the detections that actually correspond to a true prediction, over all of the predictions made in the data set, versus recall is the true positives over the total number of actual positives in the data set. And the definition for a true positive is defined via our loss function, or via the same metric as our loss function, which is intersection over union. So if the intersection of the ground truth and the predicted box is higher than 50%, then we count that as a true detection. So we compared these results to 2 state-of-the-art methods, PyClip, which we're kind of referring to as the naive approach, because PyClip is an open source Python software, Python library for direct imaging of exoplanets, and it uses the CLIP algorithm, which uses principal component analysis, matched filtering, a subsequent series of steps in order to detect the planets in the image. There's a ton of parameters that you have to tune. So the reason we're calling this the naive approach is because the results from this are essentially putting the data set through PyClip with minimal tuning. So not going through and manually tuning all of those parameters through that process. In comparison, we're comparing it to the results, the winning results from the Starshade Exoplanet Data Challenge. So a note on that, both of the teams that competed in the data challenge did not use machine learning approaches, they used conventional approaches. So they did require quite a bit of manual tuning, but were able to get really good results, as you can see, versus YOLO V3 had a little bit higher precision and then much better recall. And so I guess a note here to maybe temper some of these results is that because our data set is still relatively small, there is probably a degree of overfitting in these results, but even accounting for that, we can see that we are at least on par with those expert results that we're seeing from some of these state-of-the-art algorithms. And then just to conclude, so future work, there's quite a bit of work still to do here. So the primary first step towards improving the robustness of our CNN is to increase our training data set size. So This is either through simulating more images using Sister or other methods to artificially inject more planets into the current data set that we have to diversify it. Additionally, what I've been working on this quarter and hoping to have results early next quarter is modifying a CNN architecture to, instead of regressing the bounding box of an exoplanet, actually just directly regress the centroid of the exoplanet, since because the planets are so small in the image, we don't really care about the bounding box as much. Additionally, looking a little bit further into the future, we want to incorporate a multitask CNN architecture so that we are not only just identifying the location of the planets in the image, but also extending this to further characterization. So the planet flux ratio, studying the exozodiacal dust and understanding its distribution in the image. Finally, something that's exciting and I guess following a little bit in Jeff's footsteps, is we're looking into developing a new extensive data set that can hopefully be used as the basis for a machine learning competition hosted with ESA, as we have done with Speed and Speed Plus in the past. So yeah, that's basically the update of what I have been working on recently in post-reform.